All right, so in a previous conversation, we talked about cyclohexane and cyclopentane and cyclobutane and so on, cycloalkanes, right? And we appreciated that the most stable form of cycloalkane is cyclohexane. And so I want to talk a little more about that. Now, cyclohexane can actually get into different conformations, and I made a point of that in the last conversation, but let me go here. I've made a model here, and this is called the chair conformation, and it's called the chair, I guess, because you might, maybe if you twist it like that, can you see, like, this is the back of the chair, here's the deck and the person's feet sitting down here, okay? That's called a chair conformation. And in the chair conformation, all of the carbons are staggered, and I showed you this in the last video, right? That's not eclipsed because it's not a dihedral, right? You see that? It looks like it's eclipsed, but it's not. Okay, so but let's look down that. Let's look. What I'm going to do is look down this bond right here and see that that dihedral is staggered, right? Let's look at another one. See, they're all staggered. Okay, so this is the most stable, and it's most stable because there's no ring strain, so the angles are all 109.5, because if you look at it like this is 109.5. And there's no torsional strain because everything's staggered. I know I'm saying the same thing over and over again. Okay, so that's the chair conformation. Now we're going to draw. It's important that you get your eyes used to looking, because we can't always pull out a model or pull up a web server and build a model for it, right? So we need this notation. This is the chair conformation. It's the same thing as we have right here. Okay, that's the same thing. So let's go back here. Now the boat conformation is when it's when the two ends are actually pointed up, and I made one of those too. So let's go here, file, import molecule, XYZ, boat. Okay, now watch this, clean up, generate bonds. Watch this. Can you see that what we've done is we've twisted these two? So it's like it was like the chair. Here was the chair, but we took the person's foot and we pulled it up. Okay, or I don't know, that would hurt, wouldn't it? I guess we're talking about the chair itself would get pulled up, and this is called boat, and you might be able to see why it looks maybe like a boat if you look at the black line on here. Okay, so that's the boat conformation. We have two problems here. Number one, everything's eclipsed. Well, not everything. That's not eclipsed, right? But there's these guys here are eclipsed, and these guys here are eclipsed. And the other problem is that these two hydrogens up here are banging heads, right? There's two problems with that, and that's a relatively high energy conformation. That's the boat conformation. Let's go back here. That's that conformation right there, okay? Now there's also a twist boat. I made one of those too, but we won't look it up. I think you already get the point that it's got slightly different angles, relieves some of the torsional strain, and then there's also the half chair where it's flat except the head is up, okay? So the differences in energy are given here, and they show what? They show that the chair is the most stable, as we would expect, all right? So having said that, one last point, we've said this over and over again, I guess, that the reason why cyclohexane is so low in energy is because there's no angle strain and because there's no torsional strain. All right. Now, if you look down these two bonds right there, you can see that this would be the Newman projection for it, right? Now I'm going to pull this back up. You need to build this. Oops, let me get the cycle. Let me get the. You need to build this with your model set. Don't not build it and say I can't see it. Right? The temptations go, well, I'll figure it out with the book or whatever, but don't do that. All right. So look at this. We're gonna go look down. Now we're gonna take this. Here's the chair, right? You recognize that? Flipping around too fast. There's the chair, right? You see it? Okay. Now we're gonna look down those dihedrals. Let's turn it this way. We're gonna look down this angle, or this bond, and this bond, which is what this is saying. Looking down those two bonds, you see that? We're looking down those two bonds. Then if we look down this bond and that bond, we can see, aha, we can draw a Newman projection formula for this, right? There's the front carbon, the back one's back there. Here's the front carbon, the back one's there, right? So these guys come down, this guy goes up, right? The hydrogen goes over there, the hydrogen goes over there, all right? That's so you can see that the Newman projection formula, look at that, is that, right? Where you've got a carbon coming down. Now we don't draw the carbons on here, or the hydrogens on here, because we slip into lined line bond structures over here. The only reason we draw the hydrogens here is to show that they're staggered. All right, so get used to that. Maybe you should draw a Newman projection formula before you stop thinking about this conversation. I can see you being asked on a quiz or exam to recognize, to say, what if this is that, then what is this, and so on. All right, good luck.